In this video, we're going to learn how to find the volumes of solids of revolution, which is rotating a region between two curves about x-axis. Now let's have a look at the picture. Here on the right hand side, I have a blue shaded part, and you can see that this is going to be rotated about the x-axis. And when you rotate it about the x-axis, you will actually kind of get this kind of shapes here on the right hand side here, and which actually has a hollow part in the middle. So this part is hollow. So I'm going to use the left hand side and show a little bit what it looks like. So slightly different from the picture that I draw here. However, it will still give you a similar visual impression. So now you can see that region between a curve and a straight line is rotating about the x-axis. And I'm going to show you the curve is actually creating this shape, but the inner solid is this. So if you look carefully, if I turn it a little bit around, you will actually have a hollow space inside. So let's go back to the right hand side pictures that we got here. So we're going to again use the disc method. So that means we're going to cut the slices vertically because it's rotated about the x-axis. So if I cut the one slice of disc out, this is what it looks like. You got the center hollow, but this part is actually solid. Okay, now again, this is a cylinder. So if you turn this disc facing yourself, you will see a circle. You have an outer circle, you have an inner circle. It's like an inner circle is actually taken out. Okay, so therefore the area, the cross-section area is the outer circle minus the inner circle. So we're gonna actually use this to help us to find a cross section, and then gonna multiply by the depth of the cylinder. So let's have a look at here. We have f of x that is starting from the x-axis, goes straight all the way up to touch the top curve that we see here, and this is our f of x, the outer circle's radius. So I'm gonna call it R1. And then we have, again, starting from the x-axis, go straight up, touch the edge of the curve, which is below it, below the other one, which I call it g of x. And we're going to say this is my radius 2. Okay, so therefore my cross-section area is pi r1 squared minus pi r2 squared. Now I can take the pi, factorize the pi out, so I have r1 squared minus r2 squared. So I'm going to replace the r1 and r2 with the functions that I got. So it's f of x squared minus g of x squared. So that is my cross-section area. And for each disk, this is cross-section area, but it has a depth. So if you look at the depth, in fact, the depth is actually the change in x. So therefore, I can say for each disk, the volume is pi f of x, that whole thing squared, minus g of x, the whole thing squared, times by delta x. So based on this, that's one slice, so we have to add everything up. So you can see on the graph, both curves start from A and finish at B, so that is our boundary. So I'm going to say the volume of the solid is integration of A to B pi times by the difference of the square of the radius, which is f squared minus g squared, delta x, so I can rewrite as dx. Let's have a look at this example here. Find the volume of the solid generated when the region between the graphs of the equation. So I got a two equation here, and I draw the curve that shows that it's between 0 and 2. So the top one is my f of x, and the bottom one is my g of x. Now, if I rotate about the x-axis, you can see on the left-hand side, there's a animation is here as well, so you can roughly see what it looks like. And definitely in the middle is a hollow, there's a hollow part. And if I use the pencil to draw the picture, so it roughly looks like the hollow part, looks like a cone that will be out. And then the outside curve will also create another solid, but with the cone shapes out. So that's briefly what it looks like. Now we're going to cut these into a small, thin discs. And we need to find the cross section, which is the shaded part here, which is a big circle area minus a small circle area. And firstly, from the top curve and all the way to the x, this vertical line represented by f of x is the outer circle radius. And from this edge all the way straight down to x-axis is our inner circle radius. Therefore, the cross-section area is pi r1 squared minus pi r2 squared. So therefore, it is pi, take factorize pi out. So we have f of x whole thing squared minus g of x whole thing squared. So that's our cross-section. And the depth of the cylinder is the change in x. So therefore, the entire volume of the solid is integration. We have given the boundaries, which is starting from 0 and ends at 2. Pi bracket f of x squared, which is x squared plus half squared minus g of x is x squared. And delta x, we're going to replace it with dx. So now we continue. Do it. Expand everything, take the pi out. So x squared plus half x squared minus x squared will eventually give us x to the power 4 plus a quarter dx. All we need to do is integrate it. So therefore you have x to the power 5 on 5 plus x on 4 from 0 to 2. And now we're going to substitute the upper value, which then minus by the substitution of the lower value, which is 0. Then the final answer will be 69 pi on 10 unit cubed.